Okay. All right. So we're talking about oxidation reduction reactions, which is shorthand is redox reactions. So all four of these types of reactions are just different kinds of redox reactions. So what the heck does that mean? So oxidation is loss of electrons. Reduction is gain of electrons. Okay? So when you're talking about oxidation reduction reactions, we're talking about the exchange of electrons from one species to another species, right? They never occur by themselves, they always occur together, right? So if you have somebody losing electrons, you must have somebody gaining electrons, right? So that's why we call them oxidation reduction reactions, because they only ever come together. Does that make sense? Cool. Okay, so when we're talking about oxidation and reduction reactions, I think there's a couple of reactions that make it easiest to see what we're talking about. So the first one I'm going to talk about is single replacement. So here's an example of a single replacement reaction. We have zinc solid and copper chloride aqueous goes to zinc chloride aqueous and copper solid. Sorry, got a little ugly there at the end. Okay. So what's the first thing we do after we write a reaction?
You just tally each of the elements.
We got to make sure it's balanced, exactly, right?
Balanced. Try to get the same number.
So we have one zinc on this side, one zinc on this side, one copper on this side, one copper on this side, two chlorides here, and two chlorides here, right? So we're good to go in terms of balancing.
Yes.
Cool?
Yeah.
All right. So the next thing we want to do is figure out the oxidation numbers for all atoms in the reaction. Okay, so oxidation numbers are basically a way that we can keep track of where the electrons are and where they're going. There it is. Does that make sense, guys? I mean, maybe it doesn't make sense yet, but you're okay with it?
Yeah.
Cool.
Yeah.
All right, so I'm going to move on to the next page. All right, so oxidation numbers, and we'll come back to that chemical reaction. There's some rules, okay? We are going to go over some of the simpler cases. If you are going on to the organic section, you'll see maybe some more complicated versions of this. But for our purposes, we're just going to look at these two types of oxidation numbers. So the first one is if you have an element, your oxidation number is 0. Okay? So, as an element, your oxidation number is 0. Now, just to point out, guys, if we're talking about a metal, right? Most metals have their elements in solid form, right? So this would be the elemental version of zinc. You with me? Mm-hmm. Yeah. But a lot of non-metals tend to be diatomic, right? So for some of the non-metals, like say oxygen, right? This would be elemental oxygen, right?
Yes.
Does that make sense?
Mm-hmm.
So here, the oxidation number for zinc would be 0, right? The oxidation number for oxygen here would also be 0, okay? You guys on board with me so far? Cool.
Yeah.
So the other one that we'll talk about is if you have an ion, the oxidation number, whoops, is the charge. Right? So anytime you have an ion, the oxidation number is the charge. So we were looking at this ionic compound, right? How do I know it's an ionic compound?
Has a metal and a non-metal.
Exactly. It has a metal and a non-metal. Is everybody with me on that?
Yeah.
Cool. So if I break these guys apart, right, I know that copper is going to have a 2+. How do I know that?
It's 2 away from the no. Well, it's 1 away. I don't know.
So,
Chlorides?
yeah, exactly. So there's chloride hooked up with it, right? And each chloride has a -1 charge, right? So if you have 2 of these guys, each one has a -1 charge, then copper must have a +2. Okay?
Right.
You picking up what I'm laying down?
Yeah, it's like working backwards.
Yes, exactly, exactly. Yes.
Got it.
Everybody with me on that?
Yeah. Thank
Cool.
you for
Yeah,
that.
yeah, no, totally. It's been a while since we've talked about ionic compounds, so we got to come back to it. But when that was like when we were together, back in the days when when we saw each other in person and we left the house. Oh, I hate this. Okay, so anyways, oxidation numbers. So for oxidation numbers, we're always talking about the oxidation numbers for the individual atoms, right? Or ions in this case. So the oxidation number for this guy is just the charge, right? So the charge is +2. The oxidation number is also +2.
Oh, okay.
Okay? So then what's the oxidation number for chloride?
Is it -1?
It is. Yeah. Killing it. Right?
Okay.
Okay.
Cool. So questions about that? It takes a little bit of practice for it to stick, but this is the basic idea of what we're getting into.
Can
Okay?
you repeat that? My internet cut out a little bit.
Oh, sorry. So if you have an element, then your oxidation number will always be 0. If you have an ion, the oxidation number is always the charge on the ion, right?
Yeah.
So let's return to our chemical reaction, our single replacement. All right. Question?
Yeah, do you have to put, like, that it's a solid and that it's an aqueous solution and that do you have to put its form?
The phases, yes. Yeah.
Okay.
Yeah. It's not going to matter as much to us right now, but it will later on.
Okay.
So when we get into solutions, then we'll be dealing with, sorry, I'm trying not to throw up right now. I'm really sick. Fuck, what were we talking about? Oh, shoot. Sorry.
The phases.
Phases, yeah. So when we get into solutions, then it's going to matter whether or not you have aqueous, solid, gas, because it's going to tell you about whether or not your reaction is going to form a solid, it's going to form a gas, stuff like that.
Gotcha.
Yeah.
Okay.
So, and it's unfortunate that we don't have the lab to accompany this, because the chemical reactions in the abstract are kind of like, what? But literally you can imagine that this is a solid piece of zinc, right? So a piece of metal in this copper solution, right? And what's happening is the zinc is essentially being eaten up and then made into this zinc chloride, and then the copper is forming a solid on the outside of the zinc.
Oh, crazy.
Yeah, it's pretty cool. And I'll link to some videos in the reactions lab that we do. But
that would be really cool.
yeah, if you look up single replacement reactions, there are tons of videos. I can definitely put some videos up for different reaction types, but yeah, no problem. Yeah, I know it's really hard to talk about chemical reactions when you don't get to see them. This is kind of the reason I know a lot of people are frustrated that we're not doing labs over the summer, but like this whole lab thing that we're doing right now is like a total emergency stopgap measure, and I think you guys can hopefully appreciate now that not having a lab is kind of detrimental to a chemistry class. So
Yeah, for sure.
yeah. Okay.
So when you say the zinc is being eaten up, do you mean just dissolving?
Yeah, exactly. Yeah. So basically, when the zinc goes from a solid to an ion, right? The solid zinc is not able to dissolve in water, right? So if you just had a piece of zinc sitting in water, it wouldn't dissolve, right? But if the zinc is hooked up with the copper, then the copper has electrons missing, and the zinc is going to give the copper electrons, which is what we're going to talk about with this oxidation reduction, okay? But before we get there, let's just talk about oxidation numbers, and then we'll get to the bigger picture. So going from here, what is the oxidation number of zinc?
Oh, it's 0.
0, right? You guys all on board with me there?
Mm-hmm.
Over here, this is the trickier one. What is the oxidation number of zinc on this side?
+2.
+2. Yeah, exactly. Okay, so going from 0 to +2, what had to happen in terms of electrons?
It gained 2 electrons.
Did
No, it lost 2 electrons.
It lost 2 electrons. Does everybody see that? So we went from 0 to +2, which means we had to lose 2 negatively charged electrons. Right? So when we lose electrons, which one is that? Oxidation or reduction?
That's oxidation.
That is oxidation. So in this reaction, zinc is being oxidized.
Gotcha.
Bueno.
Questions about that? All right, so now let's look at copper. So copper, right, over here starts out with what oxidation number?
+2.
+2, exactly. Right? And over here, what's the oxidation number?
Zero.
Mm-hmm. Because it's in its elemental form. Right? So going from +2 to 0, what had to happen in terms of electrons?
Lose 2.
Reduced.
Reduced. We had to gain
Gain.
electrons, right? Which is reduction. Right? So copper is being reduced. Yes, Victoria. Does that make sense, guys? Kind of, sort of?
Yeah,
Cool.
It feels like everything is like backwards. Like I'm really good at math.
Yeah.
But it feels like this is like everything that I've learned about math. It's like question this, Jessica. Question.
Well, it's okay. So if you were to imagine it in terms of a chemical, or excuse me, in terms of a math equation, right? This would be the equivalent of adding 2 electrons, right?
Yeah.
So you're adding a negative, which is actually subtracting, right?
Yeah.
That's why it's weird. But I think about it more in terms of, so if you start off positive and you go to 0, right? Then you had to gain negatives.
That's the way I've been thinking of it.
Yeah.
Like on a time, like on a number line.
Yeah. So, and this is, I think this is helpful for most people. Is I literally will draw out a number line, right? So starting at 0, right? If I'm going -1, -2, -3, right? If I'm going in this direction, right, I have to be gaining electrons, right? If I have +1, +2, +3, right? If I'm going this direction, I must be losing electrons. Right? But I don't have to start at 0, right? There's no rule that says that I have to start at 0. I could start out at -2. If I'm going this direction, right, I'm always losing electrons. If I'm going this direction, I'm always gaining electrons, right? No matter what number I start at, the directionality is telling you whether or not you're gaining electrons or losing electrons. Does that help? I think that the visualization is important in these.
Yeah, for sure.
Other questions about that? We do another example. Cool. So let's do beep boop beep boop. Let's do a little more complicated one here. All right, so let's look at this guy. Oops, I forgot a phase. Sorry. So we haven't talked much about acids yet, but this guy is an acid, specifically hydrochloric acid. And acids tend to be pretty good at dissolving metals. We'll talk a little bit more about why this reaction occurs in just a minute, but I just want to talk about how this stuff happens for now. All right, so what's the first thing we always want to do when we're looking at a chemical reaction?
Balance.
Balance it, right? So I have 1 magnesium on this side, and 1 magnesium on this side. Chlorides, I have 1 on this side and 2 on this side, right? What could I do to balance the chloride?
Well, your hydrogen is off also, so I would put a 2 in front of the hydrochloric acid.
So put a 2 right there?
Yeah.
Cool. So now this gives us 2 chlorines, and our hydrogens are 2 on this side and now 2 on this side. Remember, this 2 out front applies to the whole thing, right? So there's 2 hydrogens and also 2 chlorides here, right? Okay, so now we're all balanced. So now we want to talk about the oxidation numbers of each guy. So, oxidation number for magnesium solid. Oops.
0.
0. What about hydrogen over here? So we haven't talked a lot about these, but in an acid, hydrogen out front is going to act like a metal cation. Oops. Okay. So, this is kind of elucidating why hydrogen is written as a part of group 1, even though we say it's technically a non-metal, right? What do group 1 metals have as a charge? +1, exactly, right? So hydrogen is +1 here.
So does it matter about the 2 in the front or no?
No, it doesn't. The oxidation number belongs to the atom or the ion, not to the chemical reaction. Does that make sense?
Yeah.
And the oxidation number for chloride? -1.
-1.
Okay. And now, everybody with me? Cool. Now, magnesium on this side, what's the oxidation number?
Still 0. Oh, no, it's +2.
It is +2. Right? And chloride?
Is -1.
Mm-hmm. And what's the oxidation number for hydrogen gas?
Someone else answer.
0.
It's 0, that's right, because this is the elemental form of hydrogen. Awesome.
Oh. I was going to say 2.
Okay.
All right. So now that we know the oxidation numbers, one thing that I want to point out here is that when you see somebody like chloride who's on both sides and hasn't changed, you can just kind of ignore them, right? So in an oxidation reduction reaction, the action is all about who's gaining and who's losing electrons, right? So if somebody's oxidation number doesn't change, then they are not a part of the reaction. Does that make sense? They're what we call spectators. They're just along for the ride. So, looking at magnesium, right? We went from 0 to +2, right? So we had to be losing electrons, which means that magnesium was oxidized or reduced?
Oxidation.
Oxidized, exactly. And so looking at hydrogen, right? Hydrogen started out at +1 and went to 0, right? So what happened to it?
It gained electrons, which means it was reduced.
That's exactly right.
Yeah, the number line helps a ton.
I really think the visualization is helpful. I tell students to write it down every time you're doing these problems, because it's really hard to think about electron math because it's got a lot of opposites. And I think that that makes it confusing, but when you visualize it this way, as long as you don't accidentally draw the arrows going in the wrong direction, right, which could definitely mess you up, but as long as you draw your arrows correctly, I think starting out at 0 and picturing what happens if you go to the negatives makes it easier to see that you're gaining electrons, and starting out at 0 and going with losing electrons must be the other way, right? So that's why I think it's helpful to do the number line when you're trying to figure these out. Okay. Questions about these guys? We're all right? Awesome. All right, I'm going to take this guy